Derivatives of trig functions. Essential question. Can I find the derivative of trig functions and apply it? Let's start with f of x equal to sine of x. Let's graph the sine of x and then see if we can predict the derivative. All right, the sine of x looks something like this. Remember that its amplitude is 1 and that its period is 2 pi. What's important to note is where the horizontal tangents are. That's going to tell us something about the derivative at those points. Okay, between this point and this point, we can see the derivatives are all positive, with the greatest being right here at 0. And over here, all the derivatives are negative, with the greatest being at pi. Now this looks awfully suspicious. This looks like cosine x. Let's go ahead and use our calculator. I have put sine of x and I put the derivative of y sub 1 to take a look at what's going on. Here's my sine of x. And now we're going to have the derivative. Every point graphed is the slope of the tangent line for sine of x. And it's doing just as we predicted. And we can see it looks an awful lot like cosine. All right, in the course of what I'm going to be doing today, we're going to be using some identities, especially this identity. We're going to use this identity. We're going to use it this way, though. We're going to use it as secant squared theta minus tan squared theta is equal to 1. And we're going to use the Pythagorean identity here. All right, so let's prove our suspicion. F of x is equal to sine of x, f prime of x is equal to cosine of x with the definition of derivative. Here's the definition of the derivative right here. And our function is sine, so you can see I have sine of x plus h minus sine of x. Okay, this is where we're going to use the identity of the sine of the sum. Remember before I had a sine of a plus b. And so we're going to use that identity. We're going to expand it. It's going to be this right here. And I'm going to rearrange the three terms. I'm going to put this term and this term together, and then this term over here, and separate the fractions. Now I'm going to factor out the sine and factor out the cosine. The limit of a product is a product of the limits. The limit of the sum is the sum of the limits. I'm using those limit theorems. And this limit ends up going to 0. And this limit ends up going to 1. So this whole quantity is 0, which means the limit of cosine of x as h approaches 0. Remember, there's no effect because there's no h here. The answer is cosine of x. So we've proved it with a definition that indeed our suspicions are true. All right, so let's write this down again. The derivative of sine of x is equal to cosine of x, and use it to differentiate. Y prime is equal to x squared, and I'm going to use the product rule, so I'm going to find the derivative of sine of x plus the derivative of x squared times the sine of x. And we just proved that this is cosine x, and this is a power rule, 2x times sine of x. All right, now we're not going to prove this, but we can use a calculator to validate. Let's go ahead and put in cosine of x instead of sine of x and graph its derivative. According to the rule, it says the derivative should be negative sine of x. Let's see if this does happen. So as the calculator graphs, it's graphing, each point that it graphs is the slope of the tangent line for the cosine of x. And sure enough, that red curve does look like negative sine of x. Okay, let me go ahead. With these two derivatives, I can actually prove the rest of the derivatives for the other trig functions here. So I'm going to use the quotient rule, and this is going to be cosine of x times the derivative of sine of x minus sine of x times the derivative of cosine x all over cosine squared x. Now the derivative of this is cosine, so this will be cosine squared x. This will be negative sine of x multiplied by sine of x preceded by a negative, so that's plus sine squared of x all over cosine squared of x. This is an identity in the numerator, 1 over cosine squared x, and we can write it as secant squared x. And so that's our three derivatives. So let's go ahead and list them. Here's the three. Here we proved with the definition. Here we validated with the calculator, and here I just proved using these two previous derivatives. All the rest of these derivatives can be proved just like I did with tangent x using the quotient rule. Now try to look at some patterns here, sine and cosine. Look at the patterns of tangent and cotangent, and notice one is positive, one is negative, and you notice the pattern with cosecant and secant. Both cosecant and secant have the same identity in the derivative times something else. All right, let's go ahead and differentiate this. This requires us to use the quotient rule, so that's what's happening here, quotient rule. And then the derivative of this is here, and the derivative of this is right here. So we're going to factor out the secant x. We're going to take a secant x out of both of these, and then I'm going to distribute the tangent, so I get this. Now here's that identity I was having you to look for. That's going to be a 1, negative 1, and then we have this. So I'm looking at when the derivative equals 0. The only time derivative is going to equal 0 is if the numerator is 0. And that's not going to happen here. Secant of x will never equal 0 if you remember what the curve looks like. So I'm going to set the second factor equal to 0. And that happens at pi fourths. Okay, so it happens right here at pi fourths. And it also happens over here, revolving pi units. So we'll say plus n pi. So these will be all the places at which it occurs. All right, let's take a look at using it with a spring. And here's our spring model for displacement, and we'd like to find the velocity and the acceleration. So velocity, remember the derivative of cosine is negative sine, and let's take a look at that. So here's my velocity curve right here. So right here, the slope of the tangent line is 0. You can see these are negative values right here until we get here, which is 0. So it's following just what we suspected it would do. An acceleration, derivative of sine is cosine, so this is negative 4 cosine t. And so this represents the slope of the tangent lines for the velocity curve right here. All right, find the 27th derivative of cosine x. So here's the first, second, third, and fourth. Notice that the fourth is the same as the first, and then you start repeating yourselves. So multiples of 4, our derivative will always be cosine. So if we start right here, and then we can find the 25th derivative, which we know is going to be negative sine of x. And then we can find the 26th derivative of x, which we know is going to be negative cosine of x. And the 27th will be sine of x. And so that's how to find it without going through each derivative. All right, let's go ahead, and there's always going to be limits involved, especially when we're working with derivatives. Let's rearrange this limit. So I'm going to write 1 over 4, and I'm going to keep the x down here. I'm going to multiply by 7 over 7, which is a 1. This becomes 1. And this is 7 times 1, which is 7/4. Let's take a look at the limit as x approaches 0 of x times cosine x over sine of x. I can rearrange and have x over sine of x times cosine x. I know that this is going to go to 1, and as x approaches 0, this will be 1. Your turn. Go ahead and stop the screencast, try these problems, and I will go ahead and show you the answers. All right, let's try again. Here's another 4. You're going to use product rule, quotient rule, power rule. Stop the screencast, try the problems, and then look at the answers. And this is the end of the screencast.